Hello, hello, hello. How's everyone doing? I'm sorry I canceled last stream. I was really tired that day. I haven't been able to, well, went on Monday. I haven't been able to sleep for like 3 days in a row. So I was really tired. And then also, my collaborator also could not stay awake either. So it worked out, but I'll be replacing that stream with something on the weekend. I might be streaming twice over the weekend, or maybe once on Friday. I don't know. That I'll figure out, but I'm super excited because this will be my last physics stream for the year, I guess, because I'll be going hiatus for a month. And I'm really excited because we're finally getting to like what feels more like real physics. I know the previous chapter was just vectors and it kind of just felt like vector math, which it was. It was totally vector math, but physics is basically vector math. And I'm really excited to actually finally move to like position, displacement, and velocity. I was looking a bit through chapters, so we're on chapter 3. I didn't post the link on Twitch, but the book is open source. This website has amazing open source textbooks just in general. If you like to follow along, feel free to. This is a fun, no stakes physics study session. Let's pin the message. Yeah, that's the physics textbook if you like to follow along. But yeah, I might stream tomorrow. That will be a gorilla stream, and I might stream on Sunday or Saturday. That will also probably be a gorilla stream if I do. If I stream tomorrow, I will be singing. If I stream on Sunday, I'll be playing Night in the Woods. So, yeah. Oh, and big announcement, I guess, sort of big announcement, that karaoke stream that I've been like hyping up for a month and a half now. Yeah, I will release a post tomorrow talking about the theme. But if you're at the stream now, I'll announce the theme now, but I'll make an official post on it tomorrow. The theme is Nightcore. I don't know if anyone could pick up on that, but I'll be singing Nightcore, a few Nightcore songs, and then other songs as well. And when I say Nightcore, I mean I will actually be singing with the instrumental pitched up and it being faster, which means I have no time to breathe, and I have no air. I can't breathe, and everything will be at a much higher pitch. So it won't sound the best, I'm gonna be honest. I've been practicing. I'm like, okay, I feel like I'm at my skill limit at the moment, and at my blue human robot bear limit, to be honest. So some of them will sound a bit funny. But other than that, I'll have a good time, and I'll include songs that I am more comfortable singing into it as well. So if I do stream tomorrow, I'll be practicing for my Nightcore karaoke, and I'll release a sort of like promotion. My Nightcore karaoke will probably be Tuesday of next week. And then I'm gonna be gone for a hiatus for about a month. And I'll be back in January. I might be back at the end of December. The very end of December. But I have to see what's going on. But yeah, okay, I'll stop talking and I'll get into the physics, because I'm excited. We finally get to like what feels like actual physics. My plan for today is to learn about position, displacement, and average velocity. And then, depending on how much time or how long this takes, I might start on instantaneous velocity and I'll stop there. And then the next time we'll do speed. But if I don't have enough time, I will finish 3.1, which is position, displacement, and average velocity. And I'll save instantaneous velocity and speed for another time. Yeah! I hope everyone's doing well. Okay. I have not said anything yet. I have not read the introduction of this chapter yet either. So let's read that. Chapter 3, Motion Along a Straight Line. Introduction. Our universe is full of objects in motion, from the stars, planets, and galaxies, to the motion of people and animals, down to the microscopic scales of atoms and molecules. Everything in our universe is in motion. We can describe motion using two disciplines of kinematics and dynamics. We study dynamics, which is concerned with the motion in Newton's laws of motion, but there is much to be learned about motion without referring to what causes it, and this is the study of kinematics. I hate kinematics. Kinematics involves describing motion through properties such as position, time, velocity, and acceleration. The full treatment of kinematics considers motion in 2 and 3 dimensions. For now, we'll discuss motion in one dimension. So the 2 and 3 dimensions, if you remember from previous lessons, is when we talked about vectors. So vectors comes into this a lot. I'm considering engineering in the future. Would you recommend it? Doesn't matter what school one goes to. It depends. For me personally, it's like, for engineering, I think it depends what you want to get out of it. Like, what do you want to do? Do you want to build? How do I explain it? Let me think. Like what, I guess, what do you want to do with your life? I know that's a very loaded question, but like, what do you want to do with your life? Some people who like science, sometimes I would recommend them going to the more natural sciences versus engineering, because that's what they're more passionate about. But other people prefer to have something like, I don't want to say more tangible, because it's not like natural sciences aren't tangible, but it's like, what do you want to do? What matters what school one goes to? As long as your school is accredited, no. I don't think it really matters what school you go to. Most of the stuff you learn in engineering for, like, let's say the future in your job, you mostly learn it there. You don't really learn it at school. At school, you build the skills to be able to learn things at your job, but no, as long as your school's accredited, it doesn't really matter. It does look nice on a resume, but yeah. And also, yeah. Full treatment of kinematics considers motion in 2 and 3 dimensions. For now, we discuss motion in 1 dimension, which provides us with the tools necessary to study multi-dimensional motion. A good example of an object undergoing 1-dimension motion is the maglev, so the magnetic levitation train, depicted at the beginning of this chapter. It travels, say, from Tokyo to Kyoto. It's at different positions along the track at various times in its journey. Therefore, it has displacement or changes in position. It has a variety of velocities along its path and undergoes acceleration, changes in velocity. With the skills learned in this chapter, we can calculate these quantities and average velocity. All these quantities can be described using kinematics without knowing the train's mass or forces involved. Yeah, okay. There we go. Okay, I did not create a section for the introduction, so let me quickly add that. Okay, introduction. What do we learn from this section? Very insightful. I guess I just want to contribute, and I like tech. Okay, so if you like tech, then I feel like engineering would be more closely related to what you like. I was a person who liked chemistry, but I chose engineering because I felt like I could branch off to other things. You don't have to know what you want. You can always change your major depending on where you are and what school you go to. Even after you get your degree, you can always change your career path too. So there's nothing very set. But if you like tech and you want to contribute in the tech and you want to create something, I don't know. A lot of people like to work on like CPUs and GPUs. I hear that's the trend these days amongst the younglings. Amongst the younglings, for that I would recommend engineering if you want to work in like computers. Introduction. Okay, so we know what kinematics is. So kinematics involves describing motion through properties such as position, time, velocity, and acceleration. And I feel like that's very important. So we should define that and write what kinematics is. But I know a lot of people who were studying engineering and then they switched to the natural sciences and vice versa. It kind of just depends on what you like and what you sort of want to do in the future. But even then, if like you study natural sciences, it's not like you can't get into engineering career after. And like if you study engineering, it's not like you can't do scientific or like more traditional scientific research after you're an engineer. Kinematics describes the position, time, and velocity. So, we talk about changes in position is displacement. So we'll put displacement. I should make this better. I'm sorry, I haven't written on the tablet in a bit of time. Displacement is changes in position. In position. Okay, changes in position. Then we have acceleration, which is a change of velocity. It's funny how it mentions that here. Well, I guess most people have an idea of what velocity is. It's just, it didn't define what velocity is yet. Maybe it kind of just assumes. Okay, and another note is that kinematics considers motion in 2 and 3 dimensions. And we don't have to deal with that now, because we're just doing it in 1 dimension, or like a straight line, basically. And 2D. How do I do this? Ampersand. Yep, there we go. And 3D 3D. Motion. Heck yeah! I can give you a tip on this one. Don't be too focused on getting to something like Harvard or MIT. Yes. I think in terms of school, I'm not gonna lie, like sometimes bigger name schools can help you find a job more easily. That being said, it's not the end all. Like, don't focus too much on that. It's not like you can't find a job if you don't go somewhere. As long as it's accredited, that's really all that matters. Tech-related engineering is almost the same as a very engineering-focused college. A local one with 3D printers in a library is more than enough. Job market is bleak. Yes, you are right. But at the end of the day, it's not like you can't find a job. Does it look better if you go to an Ivy League? Like, yeah, of course it does. I'm not gonna lie. I do think it's easier to some sense. But if you don't make it, it's not like you can't. When you actually get to the job market, if you had any well, what if you're an old person like me, had a little bit of experience working in an engineering field, you'll meet like a bunch of people from colleges you never even heard of, and they're not necessarily the most elite, but they're very smart too. Like the interviewers will look at it, but it's not the end all. They still have to interview you, they still test you, like they still go over interview questions, and I think acing your interview questions is more important than going to a like Ivy League or something. Like, yeah, it looks nice, but and sometimes you have like legacy things, but it's not like you can't find a job. It's not impossible. Like, yeah, it's not looking too great. I'm not gonna lie, job market's not looking too great, but it's not impossible. And since you're trying to get into a college or like deciding, I don't think you should be worried too much about that. Okay, learning objectives of position, displacement, and average velocity. We made it to this part of the book. I'm very happy. I know it's only 3 chapters, and this one has like, I don't know how many chapters, like 13. We'll get through it eventually. Okay, learning objectives of this section. By the end of this section, you'll be able to define position, displacement, and distance traveled, calculate the total displacement given the position as a function of time, determine the total distance traveled, calculate the average velocity given the displacement and elapsed time. When you are in motion, the basic questions to ask are, where are you? Where are you going? How fast are you getting there? The answers to these questions require that you specify your position, your displacement, and your average velocity, the terms we define in this section. Alright, position. Position. I see it bolded, which means we should write that down. To describe the motion of an object, you must first be able to describe its position. Where is it at any particular time? More precisely, we need to specify its position relative to a convenient frame of reference. A frame of reference is an arbitrary set of axes from which the position and motion of an object are described. Earth is often used as a frame of reference, and we often describe the position of an object as it relates to stationary objects on Earth. For example, a rocket launch can be described in terms of the position of the rocket with respect to Earth as a whole, whereas a cyclist's position could be described in terms of where she is in relation to the building she passes. You have a figure of that. In other cases, we use reference frames that are not stationary, but are in motion relative to the Earth. To describe the position of a person in an airplane, for example, we use the airplane, not the Earth, as the frame of reference. To describe the position of an object undergoing one-dimensional motion, we use the variable x. Later in the chapter, we'll discuss freefall and use the variable y. Okay, position. What is position? We know that position is where something is at any particular time. Where something is at any time. Okay. And we need a position, needs a frame of reference. Needs a arbitrary frame of reference, I should say. Or a convenient frame of reference. Well, it's kind of arbitrary, right? A convenient frame of reference. Needs frame of reference. They care more about experience and connections. Exactly. Experience and connections and how well you can answer your questions at interview. Would you rather compete MIT classmates for an on-campus internship? Yeah, I don't think you should worry too much about what schools you went to. And as a person who got rejected to all the schools that I initially applied to, when I first I'm old and crusty now. But when I was a young hopeful engineer, I got really sad being rejected from all the schools I thought I was gonna get into. But it turns out, hey, it didn't turn out too bad, so I still got a job at the end later on. And I went back to school, so your path forward is never really straight. It's more about how can you learn and adapt, and what do you want in the future. Sometimes your goals change. Hello, what did I miss? You didn't miss much. We went over the introduction about what kinematics is. So kinematics just describes, I need to sneeze. Kinematics just describes motion, and then we're talking about what position is, and we're defining what position is. Ugh. Every time do physics like streams, I always sneeze so much, and I don't know why. Okay, it needs a frame of reference. So, and this creates an arbitrary set of axes from the frame of reference. So I'll put creates arbitrary set, or create, yeah, arbitrary set of axes. Ugh, I hate having the sneezes. Sorry, excuse my sniffling. Excuse my sniffling noises. Position to the earth. In other cases, references are not stationary. And then, these frame of references can be stationary or in motion. Can be stationary or in motion. How do I spell stationary? Stationary. Or in motion. Yeah. Okay. So that's position, and then let's move on to displacement. %90 CS majors. That's a lot of CS majors. I feel bad. I'm not gonna lie. CS majors at my school were very interesting. They were interesting people. Not necessarily in a bad way, but they were very interesting people. Sometimes they did not smell the best. Of course, it's not all of them, but, you know, a few bad apples ruin the bunch. Perhaps your immune system is rejecting knowledge. You know, sometimes I think that may be true. If an object relates... if an object moves relative to a frame of reference, for example, if a professor moves to the right relative to the whiteboard, then the object position changes. This change in position is called displacement. The word displacement implies that an object has moved or has been displaced. Ooh, wonder where they got that from. Although position is a value of x along a straight line where an object might be located, displacement gives the change in position along this line. Since displacement indicates direction, it's a vector and can be either positive or negative depending on the choice of positive direction. Also, an analysis of motion can have many displacements embedded in it. If right is positive and the object moves 2 meters to the right, then 4 meters to the left, the displacement are 2 meters and -4 meters respectively. Okay. There we have it. We got displacement. Change in position. So displacement is simply the change in position first. And this implies the object has moved or been displaced. Although its numerical value, the value of x, I can't read, of x along a straight line where an object has been located, displacement gives a change in position along this line. So it's a change along a line, change of position, and it's usually represented as a change along a straight line in this case because it's one dimension. So I guess in this case, change in position along a line. It is a vector, so it is either positive or negative. So it shows the value and the direction. It is a vector, so it can be positive or negative. Okay, so here we have the professor at this position. We have the position as x, and then there's a change, and they use delta x as a change. Displacement, delta x, is a change in position of an object, where delta x is displacement, and okay, so they use xf as the final and x0 as the initial position. So let's write that down as what displacement means when it comes to putting it in an equation. It's displacement. So oftentimes when you see the delta, that means that there's a change in something. So this little delta symbol means change. Displacement, xf, and x0. We have xf as the final position, is final position. And x0 is initial. Oh, it explains it right here. I didn't need to explain it. You should probably write the symbols in your notes too, not just... Oh, you mean like X and the delta? The thing is, it always changes, right? Like they said that they're gonna use free fall with the variable Y. The variable position could technically be anything you define it as. I think getting the concept was more important. But it does help a lot of people to visualize it. But it goes over it here now. But yeah, I will include the equations, just sometimes it's because it changes all the time. I don't know, that's how I think about it, but people learn differently. We use the Greek letter, the uppercase Greek letter delta, to mean change in, so I did not need to explain this because it explained it for me. But yes, this delta symbol means a change in something. So we have x as like the position, so there's a change in the position. Thus, delta x means change in position. Once again, it said it for me. We always solve for displacement by subtracting initial position from the final position. Note that the SI units for displacement is the meter, but sometimes we use kilometers or other units of length. Keep in mind that when units other than meters are used in a problem, you might need to convert them to meters to complete the calculation. Objects in motion can also have a series of displacement. In the previous example of the pacing professor, the individual displacements are 2 meters and -4 meters. Given a total displacement of -2 meters, we define total displacement, delta x total, as the sum of individual displacements and express this mathematically with the equation delta x total is equal to the summation of the changes, where delta xi are the individual displacements in the earlier example. Okay, so we define total displacement as delta x total is equal to the summation where the change in the individual displacements. So you basically add all the individual displacements with each other, and then you get the total displacement. So let's write down the total displacement equation. But for people who are not used to math, do not be scared of the Greek letters. They just represent an addition or a subtraction sign or a derivative. So they're just interesting ways of writing change in or addition. or subtraction of something. So do not be alarmed if you are not used to seeing the summation. So we have total displacement. We have the delta x total. I can't write that small. Okay, you're gonna have to deal with my not so great writing and my not so great, yeah, really everything. We have that. This is our total displacement. Let's define what the change in position for the individual displacements is. Individual so for the example with the teacher, we have as they say, start at 2, or the final position is 2, and then it goes from 2 to -2, or sorry, -2, and then you subtract the initial position, so -4. And I'm going to write that out as well. So we have a teacher who's here, or a professor in this case, here. They move to this way, 2 meters. This is not to scale. And then after, since they're right here, they move back another 4, right? What did they say the teacher did? 4 to the left. Yes, okay. They move back another 4. So something like this. Once again, this is not to scale. I'm going to try to make it look a little better. Something like that, I guess. And so this is 4 meters. And then the teacher ends up here at the end. And we want the total displacement, which, as we can visually see, is -2. But we start at position 0. So we have 1. Our first movement. So our first movement, we start at 0, and then we end up at 2, so we get 2. Then we have our second movement, which is x2. We end up at -2, and we subtract our initial position, so we get -4. And then we combine the two, so we get the sum. So change in xi plus change in x2, so equals -2 meters. And that is this. So we'll write x total is equal to -2 meters. Yeah. The total displacement is -2 along the x-axis. It is useful to calculate the magnitude of the displacement or its size. The magnitude of displacement is always positive. This is the absolute value of displacement because displacement is a vector and cannot have a negative value of magnitude. In our example, the magnitude of the total displacement is 2 meters, whereas the magnitudes of the individual displacements are 2 and 4 meters. The magnitude of the total displacement should not be confused with the distance traveled. Distance traveled, x total, is the total length of the path traveled between 2 positions. In the previous problem, the distance traveled is the sum of the magnitudes of the individual displacements. So this is going to be a refresher of last time, if you know what magnitudes are. Where did my pen go? There we go. So the magnitude is just this value. To find the magnitude of like of something, you want to get like the difference. The magnitude of displacement is you want to get that change. You want to get that displacement. So that change in x, take whatever value that is, and then you just want to absolute value it. So this is the magnitude. So for example, our magnitude here is 2, our magnitude here is 4. Magnitude does not have a direction, so it's not positive or negative. It's always, well, it's always positive, I should say, because it's absolute value. You just want the value, you don't need the negative. It's never negative. So magnitude is never negative. It's never negative, you just want to get that value. Hence the name absolute value. And to get the distance traveled, you want the length of the path. So you just want to add all of the magnitudes. So distance traveled is the length of the path, also known as the magnitudes added together. Path, which is the magnitudes added together. Yeah. And they show an example with the x total being the distance traveled. We'll define that here as distance traveled. And then for the example, they took the magnitude of the displacement and then just added it all. So traveled, added together. So you basically sum the magnitudes of everything. Can I write this? I think this is correct, right? I take the total, then I put the sum of the magnitude of xi. So that is also your distance traveled. I'm surprised they didn't write it like this. They wrote the total displacement like with a summation, but they didn't write the distance traveled with a summation. Okay, average velocity, and then, hey, we're almost done with our first section. So maybe we will. In fact, I'm going so fast that maybe we'll even get to speed. But who knows? What's the speed that I'm going at? Is the speed too fast? Alright, average velocity. To calculate the other physical quantities. To calculate the other physical quantities in kinematics, we must introduce the time variable. The time variable allows us to not only... I can't read. Let me restart that. Sorry. To calculate the other physical quantities in kinematics, we must introduce the time variable. The time variable allows us not only to state where the object is, its position, during its motion, but how fast it is moving. How fast an object is moving is given by the rate at which the position changes with time. And there we go, that's our velocity, the rate at which position changes with time. For position xi, we assign a particular time, ti. Ah, there's a fly! I hate bugs. Why are there so many bugs here? Get away! Okay, sorry. For each position, xi, we assign a particular time. If the details of motion at each instant are not important, the rate is usually expressed as the average velocity, v. There's a fly, it's back. Get away from me! This vector quantity is simply the total displacement between 2 points divided by the time taken to travel between them. The time taken to travel between 2 points is called the elapsed time. Okay, so our average velocity is represented by the v-bar. If x1 and x2 are the positions of an object at times t1 and t2 respectively, then we can get our equation of the average velocity. So let's write that down. What is average velocity? Why is it important? And what's the equation? Average velocity. I really hate flies. It's still the fly, please. No. It always flies like right in front of my face too. Okay. It's gone for now. It's gone. I hate bugs. I really do hate bugs. So, how fast something is moving. How fast an object is moving is given by rate at which position changes with time. And we have the average velocity. If the details of the motion at each instant are not important, the rate is usually expressed with average velocity. So there's like an a time period velocity or the average, and you just do the whole time. Are you hoping for the average velocity of the fly to be 0? Absolutely. In fact, yeah, really. I want it to be 0. I wish it would be negative. I wish it would just disappear. The fly could be 0. In fact, I don't want it to be here. It can move backwards in the timeline, break the laws of physics, and just simply go back to before it was born and just never be born. I hate bugs. I'm sorry if that's a bit harsh. I really hate bugs. I hate bugs so much. The thing is, if the average velocity is 0, it just means it's not really changing position with time, so it could still be alive, right? It would just be hovering there. I don't like that. I don't want it to be moving at all. So if, I guess... How do I say average velocity? If it says like this is not important, but I don't like how they worded that. I'm gonna say something else. If the details of motion at instant are not important. I should say average velocity is velocity over a large time period. I think that's better to explain it than just being like, oh, if it's not important at this time. So yeah, I'm gonna write it like that instead. So average velocity is the change in position over a larger period of time. Or I'll just put like over a period of time. And then yeah. And then we have our elapsed time, so the time taken to travel between the 2 points. So since you use displacement, you get your 2 points, have the time in between, and then that will be what you use to calculate your average velocity. So instead of having the displacement of the fly to be 0, I would like it to have never elapsed time, really. I would like the fly to have never elapsed any time. I'd like for the average velocity to be undefined, which is impossible. But, you know, that would make me very happy. So we use elapsed time to get that. That's a T, by the way, not an F. I know I can't write too well. So this is the time taken to travel. Okay, yeah. And now we can get into the equation part, which is, the way they've wrote it is very long. So I'm gonna abbreviate like this. And even then, I think it still might be too long because I have to write out displacement. I'm gonna write it like that, displacement, and then put a dot between 2 points. And here we got elapsed time. Between 2 points. And then this is equal to this, so the change in displacement, or change in position, which is displacement, over the elapsed time, which can also be represented depending on how many, like, changes there are. Sorry, depending on how many, I see, this is the thing, like, what I mean to say is, they write x2 minus x1 here, but then when you go up to here, they write it as x final versus x initial. Like, sure, 2 may not be the final position of your object, but then it's just, it's harder to get, especially if you don't understand the concept. Like, if you don't know the concept of what's going on, then the fly is back. No, shoo, ew, it touched me. Can displacement be negative? It can. It can be negative. We actually went over an example for that. Let me quickly go back to it. Displacement can be negative. Or sorry, like, total displacement. Yeah. Okay, so let's, like, because it can be negative because you can define an axis. So technically you can get a negative velocity if it, let's say, moves backwards depending on where you define your axes of which direction. But when I say negative, I mean I want the time to be negative, you know? I don't want time to exist. I don't want this fly to be here. I wish it never existed to begin with. But yes, displacement can be negative. It depends on how you define your axes with your frame of reference. Go away, go somewhere else. It keeps flying like next to my face. It touched my hand too, and I don't like that. I hate bugs. I really do hate bugs. I'm sorry for any bug lovers, but I hate bugs. I mean, I don't mean to disrespect them, but, like, I have to pay rent, so I pay rent to live inside, you know? They have all of outside where they can live, and they don't have to pay rent. Like, why you can't live in this place for free? Excuse me? Excuse me, you can't live here for free. Okay. Example 3.1, delivering flyers. So we got an example, which means we switched to purple. I love purple. I love blue and purple. Jill sets out from her home to deliver flyers for her yard sale, traveling due east along her street lined with houses. At half a kilometer and 9 minutes later, she runs out of flyers and has to retrace her steps back to her house to get more. This takes an additional 9 minutes. After picking up more flyers, she sets out again on the same path, continuing where she left off, and ends up 1 kilometer from her house. This third leg of her trip takes 15 minutes. At the point, she turns back towards her house, heading west. After 1.75 kilometers in 25 minutes, she stops to rest. So, what is Jill's displacement at the point where she stops to rest? What is the magnitude of the final displacement? And what is the average velocity during her trip? Okay, and they've given us a nice illustration to explain what happens. Oh my gosh, I am gonna go insane. This fly is... Get out! And good evening, hello! Sorry. So Jill spends Thank you for the lurk. Jill spends 9 minutes at the 0.5 kilometers, and she runs to get flyers, has to go back home. Then she goes out again, and this takes 15 minutes, and then she heads back home after heading west. Oh, I see. Okay, so this takes 25 minutes. Total displacement to the point where she stops to rest. So that would be, yes, the summation one. So let me go over the, how do I say this? The equations that we'll need to use first. I guess I should write everything down first, but the equations for the total displacement, we need to use this. So we simply add all the displacements together, and that's how we get our total displacement. The magnitude is we simply add all the distances. So 0.5 plus 0.5 plus 1 plus 1.7, and just add them all together, because for magnitude, remember, it can never be negative. It is always the absolute value, because you just need the absolute value. And what is the average velocity? For the average velocity during her entire trip, does that mean... They did it with a graph? Oh, let's see. Oh. For the average velocity, we have to add all the times together. Then take that displacement. Oh, sorry. Take the displacement of her first position and her final position. So basically, we take the total displacement and put that over all the minutes that happened. What is the distance traveled? That would be the one we just went over. This one, we take all the displacements and just add them together. Oh, see now this time it puts it with the summation, but when I come up here, it doesn't include the summation. That's really annoying. Yeah, it's just sum of magnitudes. Oh wait, the total magnitude of final displacement. Okay, I'm getting it confused. I just gotta do it. Are you ready? You're ready to do the problem with me and the book? I'm gonna follow the book because I can't do math. By that, I mean I can't do arithmetic. I can set up all the problems, I just gotta plug it into a calculator, and I don't have a calculator with me right now. Let's start the example 3.1. So we have 0.5 at 9 minutes. And I'm just gonna use an arrow to tell which direction it's going. And then you go back home. So that's another 0.5 kilometers. Also at 9 minutes on the way back. And that you go back home. And then you go 1 kilometer. And it says it takes 15 minutes? This third leg of our trip takes 15 minutes. So you got 15 minutes, and that goes back there. And then we go back 1.75 kilometers at 25 minutes. And that goes back here. So what is the total displacement? So we start at, our final position is 0.5 minus 0, because we start at 0.0. I'm going to use home as our frame of reference. So we start at 0.5. Then we have 0.5. So you go backwards, that's 0.5. And then 0.5. So that equals 0. Oops. Since we're going backwards, make sure to add the negative so that we can get that value. Then we have go backwards, then we go forwards 1 kilometer. So we're back at... Am I doing this right? Yes. Yes, I'm doing this right. Then you take this displacement value, then you go forward 1 kilometer, and then we have that. So that should equal... No, I'm not doing this right. What am I doing? No, this should be 0. What am I doing? Hold on, let me think about this. I don't think that should have a negative. Why does it have a negative here? I don't understand this. Where'd that negative come from? I think 0 would make more sense as the displacement. Well, if I define going forward as 0.5, no, then you would go backwards. They'd be backwards -1. Yeah, I don't... So this is from, like, our frame of reference? Oh my gosh! Hello! This is stupid. Why am I not understanding this? Hello, and welcome! Thank you for the raid! Shrekbeard raid! Okay, let me give you a shout out. I hope your stream went well. What were you playing or what were you doing? But hello to the people who do not know me. I am Blueberry. I am a failed engineer, clearly. And I like playing cute games and puzzle games. But I also like doing stuff with educational stuff intertwined too. Yeah. I am an actual failed engineer, but hello and welcome. I was playing Crash. Classic game. I don't know that game. I've never heard of it. Interesting. Okay. So I'm talking about displacement, I guess I'll explain. Oh, by the way, if you need a raid and dash, feel free. If you need to get water or do your stream, like, aftercare stuff, please do. I feel like I've heard of it. Is it the one where there's, like, a fox? Am I thinking about that correctly? There's, like, a fox? Let me search it up real quick. Yes, okay. It is the one with the fox. I've never played this game before. Big franchise that started on the PS1. Oh. Oh, it's a platformer. Oh, okay. Yeah, so it is the fox. Yeah, I don't really know too much about that game, to be honest. And thank you for the brain pudding, by the way. I just saw that. He's a... Oh! Is that an animal? I don't know my animals. Marsupial, an Aussie marsupial. Oh! Wait, they're actually so cute! Okay, the real life ones are really cute. But why does the other one kind of like, why does the character in the game look like a fox? You should learn about some animals someday. I should. I really should. I might be getting a pet of my own soon, too, so... Yeah, kind of weird. The actual bandicoots look really cute and really small. They look like little rodents. I know they're not rodents because you just told me they're marsupial. But the in-game looks like a fox. Well, he's stylized like Sonic. I can see that. I can see how he's stylized like Sonic. Alright. So, let me do this again. So we have our first displacement, which is, we go 5 to the right. Then our second displacement, no, but our displacement would be -5, and this would be +1. Okay, I'm thinking about this all weird. Here's the thing, when I think about things, I don't necessarily think about it mathematically first. I think about it conceptually, and then I apply that to math. But the way that the book did it just confuses the heck out of me. Because position 1 would be here, and then back. Like, I'm getting confused with the displacement and the position, and that's my problem, I think. Yes. So that's how they did it. Let me increase this a bit more. But I see how they, like, why they broke it up into a chart with this stuff. I'm getting confused between displacement and position. So that's where my fatal flaw was. My NPC blurts out. Hey, we are learning about change, which is, that's not an integral, that's the derivative, but yeah. Oh, I see, yeah. I'm getting confused between position and displacement. And this is why I'm a failed engineer. This is why I don't call myself a real engineer. Like, did I technically get a degree? Yeah. I got confused. Sometimes I don't like how this book writes things. Like, I think this book is a great resource. Like, it's open source, it's free, it's wonderful. This website has wonderful stuff. But sometimes the way it writes, it explains problems just confuses me, even though I learned this. Like, it confuses me even though I learned this before. I'm just like, no, that's not how this works. Anyways. I'm confusing position and displacement. Our position is the home, so that's our 0 position. So we move to the right 0.5, and that would be a displacement, because then we subtract it with 0. So that would be 0.5, would be our displacement of 1. Then our ending position is at 0, because we're now back at the house, right? So that's our, technically, like, on the 0 axes. So then that's how we get the -0.5, and that's our displacement number 2. I really don't like how this book explained it, but oh well, I figured it out eventually. Then we start at 0, because we're back at the house, and then we go to the right 1 kilometer. So that would be a +1, and that would be our displacement 3. And then we're at +1. So we go the other direction. (1.75), but in terms of position, since we are in the middle, it goes back to the house, which would be 0, and then it goes to the left, 0.75. So that means our final position of this would be 0.75, or -0.75, and this would be subtract 1, because we're to the right of our 0 axes. Yeah. So really drawing it out really helps, but instead of drawing it like that, how I personally would have drawn it was, I would put this I'd put like a literal axes. Here we are. This is our home. Home! And then I would write the direction. So we go to the right one. So let me put like 0. 0. We go 1. And this would be like 0.5. We go back. So we're back to 0. And then we go here to like 1. Not to scale. I can't draw. So we're at position 1. And then we go all the way back here. Something like that. 0.75. And that'd be negative. This is how I personally would have done it. I think it's much easier for me to visualize it like this versus the way that they drew the home. I would not be able to do this at all. I'm better at reading than math and science. Well, you're compensating because I can't read or write. I struggle with spelling in English, even though English is really pretty much the only language I know. So we need people who can read, and I guess I can try my best to do the math part. Alright, so we get our total displacement is basically we just add this. So our total is just add 0.5 minus 0.5 plus 1 minus 1.75, which would just equal 0.75, and I did that in my head. Negative. Oh, I missed the negative. Can't get clearer than that. Yeah, I like when pictures are more simple. I think it's easier to draw, it's easier to understand, and also I don't have to draw any pictures. You don't want to see my drawings. You really don't want to see me do art. Alright, we want the magnitude of the total displacement. So we take our total displacement, which is this, and we simply put an absolute value on it. Which means this negative goes away, so it's just 0.75 kilometers. Go make some OCs, I want to see it now. Oh, I actually, so for my little mascot of the strawberries, so I call my community the strawberries, all my followers / subscribers / you know, all that. I call them the strawberries, and they helped me with designing it, so I kind of drew like a thing, and then I got a real artist to actually draw it out. But yeah, you can see my drawing there, I guess. It's pretty bad. There's a reason why I had a real artist, I commissioned a real artist to draw it. Yep. Oh, hello! Is your name... How do I even read that? Dragon? Yeah! Yeah! Dragon, welcome to the strawberries. But I got a real artist to do it, and there's a really strong reason why. You don't want to see me draw. Okay, and then we get the average velocity. So we take our total displacement, which is what we got here. So our change in x total over the time, which we would just add 9 plus 9 plus 15 plus 25 minutes, right? That would be, oh, math. Okay. 340. 40 plus 18. So that would be 58. And then we take our 0.75 kilometers over 58 minutes. And I'm not doing that in my head. I can't do that. That is, the book says 0.013 kilometers per minute. So like, if someone actually wants to study this, I would suggest to go over the actual math. I have actually found some mistakes in textbooks before when I would actually calculate them out. They would be like, oh, the decimal place is in the wrong. It would be like a typo thing. But I would always suggest going over the aftermath. I do not have my calculator now. My trustworthy calculator actually broke down a year ago. I love that calculator to death. It survived so many years. It just broke down. You're smart. See? Yeah, my name generally is an IQ test and you pass. Oh, great. That means I have an IQ. I have 1 IQ. Thank you. I was really thinking I had a negative IQ. That means I have some sort of something, right? Yeah. Sometimes when I see a lot of numbers in people's usernames, I'm like, my brain just freaks out. I'm like, I don't know how to read this. Alright, and then we get the total distance traveled. For the total distance traveled, we need to take these individual ones and have the magnitude of that. So, total, we get 0.5 plus the magnitude of that, which would just be 0.52, but I'm going to write it out. Plus 1, plus 1 point negative. Negative. Do not forget the negative when writing out your work. Yeah, 1.75. So we just add them all, so that'd be 2,375. So that'd be 375 kilometers. Yeah. Yeah. Okay, and I'm not gonna graph it out. I make a graph of the position versus time. That's the position versus time graph. I'm not gonna graph this out. We can look at it closer though. So if we go, we go back here, we look at this part. So he goes at 9 minutes, it goes half a kilometer, and then you go back for 9 minutes, so we're at 18 minutes. So we're back at the home. Then we go forward for 1 kilometer. Then we go back the 1.7. So it's basically just this, with time. This is just the position. So you turn this graph into a graph with time. But yeah. Okay. So we will get to instantaneous velocity. I think I'll stop there. I'll stop after this section, and then I'll save the example for next time. The thing about these streams is because since I talk so much, my voice really does give out. after 50 minutes, I can feel my voice just disappearing. My air, my lungs, everything's being sucked out of me. I'm a mega genius who built robots and shit. Studied for 20 years, but then what's the point aside from being able to do stuff? Just create great things in my philosophy. Alright. Studied for 20 years. Are you a robotics engineer? That's pretty cool. That's pretty cool. I hate robotics. I am a robot, and the reason I look like this is because I failed to build one. I don't like robotics. I've always been more of a physics, materials, chemistry person. But yeah. But when it comes to physics, I'm not even good at I'm quite frankly terrible at kinematics and forces. I'm much better at the chemistry physics part of it, if that makes sense. You know, how atoms move and the physics behind that, and so that's kind of chemistry, you know. That's what I personally am more interested in. Yeah, Jill's total displacement is negative 0.75 kilometers, which means at the end of her trip she meets up 0.7 kilometers due west of her home. The average velocity means if someone was to walk due west at 0.013 kilometers minutes starting at the same time Jill left her home, they would be able to arrive at the final stopping point at the same time. Note that if Jill were to end her trip at her house, her total displacement would be 0, as well as her average velocity. The total distance traveled during the 58 minutes of lapse time for her trip is 3.75 kilometers. And then we have a extra example. Check your understanding. part 2. It's the same sort of thing, where you define a zero, you get the displacement, and remember, position and displacement are different, and that's what I confused myself with. But yeah. And then same stuff. Take the magnitude and all that. I don't do check your understandings. Actually, I think since this book is open source, I'm pretty sure you can find the answers to this. But if you ever do, like, actually go through a textbook yourself, I would suggest doing these. But I'm too old and tired, and I don't want to do this. And also, I had a day today. Today was a very interesting day. I'm just autistic about learning things. Acoustic. Is it? No, I can't read. I understand what you mean, though. Me too. Me too. I like coding and stuff. I hate coding. That's the one part of engineering that I genuinely just can't do. Even though I'm not great at kinematics and physics, I don't mind doing it. It just takes me a bit of time to do it, like extra time than, let's say, someone who does like it. I cannot code for the life of me. I failed chem. But 8 in the outer... Oh, 8 in the outer shell stuck. Ah, your valence shells. Your valence electrons. I think the stuff when I'm planning my day. If you take derivative velocity, you can get position. Yes! We're gonna get to that, hopefully. Oh, is this more algebra or calculus-based physics? So, apparently this is supposed to include calculus, but so far, from what I've read of the book, this is not really calculus. You're absolutely right that you can use derivatives and integrals to get position, velocity. I hope that goes over it later on in this book. But at the moment, this book is not getting to there yet. We'll see. This book is supposed to include calculus. It is a university level physics book. But I don't know if it actually does. I hope it does, because that'd be fun. I actually like doing derivatives and integrals. At one point in my life, I was losing it, and I would do practice problems for fun. Because that's who I am. Yeah, I'm actually... There was a point in my life where I lost it, and I would do them for fun. Anyways, we're gonna start on 3.2. Actually... You're wrong. I would love to do more derivatives. But yeah, I don't know if this book does. It's supposed to. I wish it does. I hope it does later on. Maybe not yet. Because still chapter 3. So that's also another thing. I did go over vector math. Coding really changes based on the language you code in. Yes, that is true. Oh, that's another thing. I'm gonna start learning Python next year on stream too. There's a game called The Farmer Was Here, which teaches Python concepts, and then there's a book also from the same like open source website, and I plan to go through that too. I really need to learn Python. I can't code, and I think it would be great. I'm not thinking binary for instant logs. Oh, you're one of those people. That's cool though. I could never do that. I don't think like that. Python is useful, but man, it's ugly. That's true. But everyone these days are using Python. I remember like previously, when I was studying, most people were using like C and sometimes Java, but Java is now dead, and C has been replaced with Python. It depends though. You know, I think people who code in Rust are a bit funny though. And of course MATLAB. I code actually these days mostly in MATLAB because I just use it as a very powerful calculator. You've been coding in Rust and JavaScript. Oh. Oh. Python since, yeah, that's another reason a lot of people are using Python, because you can just generate it. Rust goes so fast. I've heard of the coding language. It's kind of like Luna or Lua. So when I was working, well, I am still working, but when I was like working for engineering stuff, I was supposed to change Lua code into C++. That was part of my job. I didn't know how to read Lua code, but it seemed okay, like it was readable. The coding language I'm most comfortable with is C++. And like C. I consider like C and C++, of course, in the same family, because they are. Yeah. For object-oriented programming, yes, C++ is great. It's a great learning, it's a great language to learn with. And I'm very happy that that's my home coding language, but I don't really code in it anymore. Lua is awesome, really. Should I learn Lua? Is that something that you would recommend? Since I don't really know much about Lua. I feel like most people don't use it. I'm the worst at C++, really? But you code in Rust and JavaScript. How? Check out Love 2D. Okay, I will. Alright, I gotta stop talking. Finish this last section. And then I'll be able to rest my voice and sleep, and maybe even kill the fly that has been pestering me. Okay, instantaneous velocity and speed. Learning objectives. By the end of this section, you'll be able to explain the difference between average velocity and instantaneous velocity. Describe the difference between velocity and speed. Calculate the instantaneous velocity given the mathematical equation for the velocity. Calculate the speed given the instantaneous velocity. We have now seen how to calculate average velocity between two positions. However, since objects in the real world move continuously through time and space, or space and time, we would like to find the velocity of an object at any single point. We can find the velocity of an object anywhere along its path by using some fundamental principles of calculus. Okay, I don't see any calculus so far, but we'll see. This section gives us better insight into the physics of motion and will be useful later in chapters. Useful in later chapters. Instantaneous velocity. The quantity that tells us how fast an object is moving anywhere along its path is the instantaneous velocity, simply called velocity. It's the average velocity between 2 points on the path in the limit that the time, and I can't read, hold on. Okay, it's the average velocity between 2 points on the path in the limit that the time, and therefore displacement, between 2 points approaches 0. To illustrate this idea mathematically, we need to express position x as a continuous function denoted by as a continuous function of t denoted by x of t. The expression for the average velocity between 2 points using this notion is average velocity is equal to the position of t2 minus the position of t1 over the 2 times. To find the instantaneous velocity at any position, we let t1 equal t and t2 equal t plus the change. After inserting these expressions into the equation for the average velocity and taking the limit as t approaches 0, we find the expression for the instantaneous velocity. Exactly, I have an error. My brain is breaking. Barry, you're trying to hurt my brain. Too late. It's okay. One more section. One more, not even a whole section. Just a little part. Literally these 3 paragraphs, and then class will be released. This small little section left. That's all we got, and the class will be released. You'll be free to do all you wish to do on your own. For instantaneous velocity, I guess we have a limit. Oh, wait, there are derivatives. How did I miss this? There are derivatives. I'm dumb. I totally missed it. It was right in front of my eyeballs. Oops. Okay, we have instantaneous velocity, also known as just velocity. I totally missed it. It was right in front of my eyeballs. I'm so stupid. Sometimes I'm so dumb. Instantaneous velocity, also known as just the velocity. It's average velocity between 2 points on the path and the limit, the time. Okay, so it's the average velocity between 2 points on the path in the limit of time that approaches 0. I think I'm gonna write it like that. Limit of time that approaches 0. I'm losing my voice. Yeah, there we go. The expression for average velocity between those 2 points is that. And then if we want the instantaneous velocity, I'm just gonna write velocity. I'm not gonna write instantaneous velocity every time. When there's average velocity, I will write out the average, but I'm just gonna write instantaneous velocity. Or I'm just gonna write out velocity instead of writing the whole name. So velocity is the limit as the change of time approaches 0, where x is a function of time plus the change in time minus as x as a function of time over the change in time. And this can also be written as the derivative of our position as a function of time. So our derivative with the position as a function of time. Yeah. Okay, let me restate that. So velocity, or in this case, so instantaneous velocity, or also known as velocity, involves the change in time as the limit approaches 0, and we have the position as a function of time plus the change in time minus the position as a function of time over the change in time, and that is all equal to the derivative of the position as a function of time. Yeah. So really, you just need the derivative of the position as a function of time. So just velocity is just the derivative of as a... I really can't speak. Okay. I also need to sleep too. I think my brain is hurting. So instantaneous velocity of an object is the limit of the average velocity as the elapsed time approaches 0, or the derivative of x with respect to t. Like average velocity, instantaneous velocity is a vector with dimension of length per time. The instantaneous velocity at a specific time point, t0, is the rate of change of position of the position function, which is the slope of position function x of t at t equals 0. So this little graph shows how the average velocity between 2 times approaches the instantaneous velocity at t of 0. The instantaneous velocity is shown at time t0, which happens to be at the maximum point of the position function. The slope of the position, so the slope is also the derivative, The slope of the position graph is 0 at this point, and the fly is back. Please, just leave. Go outside. The slope of the position graph is 0, and the slope of the position graph is at 0 at this point, and thus the instantaneous velocity is 0. At other times, t1, t2, and so on, the instantaneous velocity is not 0, because the slope of the position graph would be positive or negative. If the position function had a minimum, the slope of the position would be at 0, giving a instantaneous velocity of 0 there as well. Thus, the zeros of the velocity function given the minimum and maximum of the position function. So basically, if you want to know a velocity at a specific time, you take the slope. That's it. And I'm gonna write that down. But yeah, all this graph is showing, and all these words are basically just saying if you want the velocity at a certain amount of time or a certain period of time, you just find that time and you take the slope of that change in position, or you take the slope of the position. So you have the graph of the position here, and you just take the slope. Okay, so for velocity, it's really just the slope of your position with respect to time. Yeah, that's the end of the lesson. I'm gonna do a super quick review of everything. We learned a lot, actually. You ready? Oh, and we have the intro, too. So we learned a lot this lesson. We learned about kinematics, we learned about position, displacement, and how to calculate total displacement, the distance traveled, as well as magnitude. We did an example, and then we learned about instantaneous velocity, and next time we'll learn about speed. So bring your notes if you would like to learn. But yeah, quick review. Kinematics describes the motion, and it describes it with position, time, velocity, and acceleration. So let's learn about position, displacement, average velocity. Position is where something is at a particular time. To find a position, you want to assign it with a frame of reference. This way you can numerically sort of like pinpoint where something is. For displacement, that is the change in position. So like, let's say you have a frame of reference, and then you move to the right, and then you move to the left. That sort of change from the right to the left is your displacement. So, and then you denote the displacement with a delta x, and x being position, at least for right now, because we're only on one axis. Our total displacement is just adding a bunch of the displacements. So let's say an object moves like 7 times. You just add the displacements all 7 times together, and then you get your total displacement. To get the magnitude of our displacement, you simply put an absolute value. It can never be negative, so remember that magnitudes are never negative. You just add an absolute value. And then if you want the total distance traveled, you take your displacement, you put an absolute value to each. So basically you're getting the magnitude of every time it has been displaced, and you just add them all up, and that's how you get your distance traveled. For your average velocity is calculated between your displacement between 2 points over a time period, and you divide the two. So you use what you learned from finding the displacement, your total displacement, and then you add how much time has elapsed and divide them. For instantaneous velocity, it's really just a derivative. So you have your position as a function of time, and you take the slope of that, and that is your instantaneous velocity. So the velocity of that moment, the velocity of that time that you have in your function. and that can also be represented with the limit. So we have velocity is equal to the limit as the change of t approaches 0. We have our position, which is x, as a function of time plus the change in time minus x as a function of time over the change in time, and that's just the derivative, also known as the slope of your position. Yay! I hope someone learned something. Let me draw a little happy face, because we got through the lesson. But I hope you enjoyed that. Tomorrow I might stream, like I said, I might stream my karaoke practice. I'll make a post tomorrow as well about my Nightcore karaoke. I hope you enjoy it. It's not going to sound very great because everything is going to go so fast, and it's going to be at a higher pitched. I'll be singing on to the Nightcore instrumentals, which is going to be really hard because I don't have a Nightcore sounding voice. I don't have a high-pitched voice, and also I need to breathe. But yeah, I hope you enjoyed today's stream. I hope you learned something. Like I said, my goal of streaming is really, I just hope someone learned something. I'd be very happy if someone learns one thing. I want to inspire people to try new things and learn. Maybe not necessarily physics, but I hope you can see yourself and be like, yeah, maybe I could do that. That'd be fun. For the polls, I see most people are here for the vibes, but 22% of you brought notes. Yay! 11% of you have good memory. I'm jealous. I don't have good memory. And 11% of you forgot your pen. But yeah, even if you're here for the vibes, I hope it was nice. I hope you had a fun time. I might stream tomorrow. I will probably stream on the weekends too, to make up for the fact that I missed the stream on Monday. And my last stream will be on Tuesday. That'll be my karaoke stream. I'm going on hiatus for 1 month, and I'll be back. And I will find someone to raid. I'll stop yapping. It was great. Thank you. Thanks for being here. I really appreciate it. I'm always so nervous when it comes to these sort of streams because I feel like they're not really the norm in a way, if that makes sense. I don't know how to explain it. They just make me so nervous sometimes. But yeah, I'm gonna find someone to raid and get the raid message. Let me get the raid message first. For manga, I just finished Promised Neverland. Manga? I haven't read. The only manga I've sort of been reading was Apothecary Diaries. I love Apothecary Diaries so much. I love Mao Mao. Most great written character, and so does Jinshi. But yeah, I've sort of only been reading that. And even then I stopped for a little bit. That, and there's this like I don't know, it's not a great manga. It's there's this girl who's supposed to be a princess, but then she beats everyone up. I forgot what it's called. Let me search up the name first. Oh, it's called May I Ask for One Final Thing. That's the English title. I read a bit of it, but I stopped. It's just fun. I wouldn't say it's like, it's not bad. I wouldn't say it's something I would enjoy all the time. It's very fun. I think if I were younger, I would like it more. If that makes sense. There's nothing bad with it. It's just, I would like it more. Okay, there's a VTuber who's in science and technology, and they are repairing their Sega Genesis. I think that'd be fun. I hope they're nice. Their name is Retro VTuber, and I'm gonna raid them. I have not raided another VTuber in science and technology because I've never seen one on, and I'm scared to raid people who are not VTubers. I worry sometimes. But yeah, we're gonna raid them. I hope they're nice. Give them a nice warm welcome if you would like to stay with the raid. And if not, absolutely do not worry. Let me get this set up first. This is who we're gonna raid. Let me switch to my end screen. Oh, I think they're soldering? I can't tell. Okay. Read in 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone!